Okay, here we are with chapter 7. Did momentum last time, and now we're going to move on to chapter 7. This is some revisiting of forces. We're going to look at forces again in a little bit more complicated manner this time. We're also going to look at torque and some other things. Really, this chapter could be called the equilibrium chapter because really the solutions are all about the idea of equilibrium. For this chapter and for some future ones, the lecture will be split into two videos. Part of these lectures were recorded in the spring when we were meeting twice, or each chapter was over 2 meetings. So that doesn't mean anything other than you just need to watch both videos if there are 2 videos for the chapter. So chapter 7, concurrent and parallel forces. So what concurrent simply means is two things happening at once. Or more than two things. So as we see in this little diagram, there are not one, but three different forces, A, B, and C, all pulling on point X at the same time. Now, we had some discussion of that in chapter 5 when we talked about things in equilibrium, like the skydiver that had gravity pulling down and air resistance pushing up at the same time. We talked about the car, which had gravity pulling down, normal force pushing up, friction force backward, engine force forward. So we've kind of seen this before, but this is going to be addressed in a slightly different situation. Again, the drive here is equilibrium. The drive here is when all the forces are balanced, the object will not accelerate. So again, we're going to have multiple forces acting on an object, and sometimes those forces act together and sometimes they act against each other. Sometimes they do both. So here we got a boat being pulled down the canal. We've got a rope going to an individual on either side of the canal, and they're both pulling. Now, in one sense, right, the guy on the left is pulling up and to the left, the guy on the right up and to the right, so that one's pulling left, one's pulling right. So there's going to be some cancelization that's going to happen with their forces because they're pulling left and right. It's kind of like almost a tug of war, and those forces are going to cancel. But they are both pulling up. And so as we can see in the diagram, the boat will move up the picture, down the canal, so to speak. And this is going to be a reoccurring theme that we're going to see in a number of these problems. There's going to be some cancelization, but there's also going to be a working together. So again, we're going to have to revisit the discussion we had in chapter 3 about vectors. Again, as I mentioned at that time, the vector chapter was very much a skill chapter because we're going to come back and use the vectors and the angles over and over again. So here, just a quick review. If we have a vector F, the black arrow, and we want to break it into a horizontal and a vertical component, or here as it calls it an X and a Y component, the red and the green vectors, we're going to use a right triangle, and you will always have a right triangle. No matter what diagonal you have, you always have a right triangle because X and Y are always at 90 degrees to each other. And so if you just draw a horizontal line or a line on the X axis and a line on the Y axis, you'll always be able to create that triangle. So you just see there up at the top a review of our trig functions, right? Cosine is adjacent over hypotenuse, so CAH, ca, CAH, like so, ca, toa. So the adjacent side to this angle, so you see the angle is labeled as A, so the side adjacent or right next to the angle is f of x, so that's the adjacent side, so we put in f of x. The hypotenuse is f, not f of x. The x part of f sub x, I should say. So f sub x over f, and then we bring the f to the other side by multiplying both sides by f. So f sub x equals the hypotenuse magnitude f times the cosine of the angle A. And we do the similar thing over here for the f sub y, only this time we're using sine, right? Sine of the angle is equal to opposite over hypotenuse. So that's the first one of so, katoa. And so the side opposite the angle is f sub y. See, this is across the triangle from the angle. I know this is review, but we just need to be sure that we're familiar with it. So the opposite side is f sub y. The hypotenuse is still f. Again, we bring the f to the other side. So now we have f sub y is equal to that f times the sine of the angle. So same thing, let's stick some numbers in. If F is 45 newtons and the angle is 35 degrees, then we're going to go through this same process. We're going to get these same results. And so F of X is going to be 45 times the cosine of the 35-degree angle. Again, it's important that your calculator is in degrees when you're doing this. and 45 times the cosine of 35 degrees will yield 36.9 newtons. Had some questions about significant figures and all of that sort of thing. When we're using trig functions like this, we generally just keep 3 digits. You know, technically this 45 is only 2 and the 35 is only 2, but we're gonna use a rule of thumb of keeping 3 digits going forward here. So that was how we got f sub x. Similar process to get f sub y, only we're using sine instead of cosine, but it ends up looking very similar. 45, the magnitude of the hypotenuse, times the trig function, this case sine of the angle. So the f sub y is 25.8 newtons pulling up and 36.9 newtons pulling over. And again, this is going to be very important because this chapter is about concurrent forces. There's going to be more than one force pulling on the object, and we're going to need to combine all of those forces in some way. And the easiest way to combine the forces is to look at them in their component pieces, the x and the y, just like that was the easiest way to add displacement vectors. That's going to be the easiest way to combine force vectors. So let's look at this little example. We've got an object here in the center. It doesn't really tell us what it is, but we've got 2 forces acting on it, F1 and F2. And F1 is pulling it straight up, 525 newtons. F2 is pulling it to the right with 763 newtons. So we've got 2 vectors acting on it. And so what we're going to need to do is combine those vectors to find out what the total force on the object is. And that's going to be pretty easy because they're both only in one direction, right? They're perpendicular to each other. So we can see pretty quickly, we're going to move this 525 over to this side, and we're going to have a nice little right triangle. We know the sides. We want to find the hypotenuse. So we do a squared plus b squared equals c squared, and we get the magnitude of the hypotenuse. The resultant force of F1 and F2 is this force resultant, 926 newtons. And then we can find the angle. That isn't shown here. I don't think, nope, not shown here. But again, that's going to be the inverse trig, inverse tangent function. Again, you can go back and review the lecture from, or just the notes, or just your homework, whatever you would prefer, from chapter 3, and you can see how to do this. So the inverse tangent of the opposite over the adjacent. So we're discussing this angle right here, which comes out to be 34.5 degrees. But for that angle, the opposite side is the F1, the 525, so that one on top. The adjacent side is 763, so that one on bottom. And if we take the inverse tangent of that ratio, that will in fact give us the 34.5 degrees. So that's fine. That's just adding a couple of vectors. We've done that before, combining a couple of vectors, I should say. Technically, we are adding them, but it's not simple arithmetic addition. But really, the point here in this chapter with concurrent forces is really the point of equilibrium. So we then move on in this situation and say, okay, so the object is being pulled by these 2 forces, and there's a resultant force to the up and to the right. So what can we do to bring this object to rest? What can we do to keep this object from moving? And what we need in that case is a force, what we're going to call the equilibrium force. We're going to need a force that's just big enough and in just the right direction to cancel out the forces that are already present. So how do we cancel out F1 and F2 with a single force? So, you know, you can go, well, I could do 525 down and I could do 763 to the left. And that's true, but that would be using 2 forces. How can we do it with a single force? And again, you could do the 525 down and the 763 to the left and build a triangle down here. Or you can take the resultant force we already got and say, this is the net force. If I want my net force instead to be 0, I need to have a same size as that force, 926, but in the exact opposite direction, right? Exact opposite direction. So this is 180 degrees, the exact opposite direction of the resultant force, which was the combination of 1 and 2. Please don't get confused. We don't have 3 forces here. We really only have 2. We have F1 and F2. But if we wanted to combine those 2 and look at it as a single force, that's where our resultant comes from. So a single additional equilibrium force, 926 newtons, at 34.5 degrees below the x-axis would be enough to cancel out F1 and F2 because it's equal but opposite to our resultant force. And again, that's what we're very interested in this chapter, is the idea of equilibrium, the idea of all the forces being balanced, and as a result, the net force is zero. And then we go back to Newton's second law. If the net force is zero, F equals ma. The net force is zero, no matter what the mass, the acceleration must be zero. The acceleration is zero, the motion is not changing. And if it was sitting still to begin with, it will keep sitting still. Now, you can also have the situation where the object is moving and there's zero acceleration, but then it will keep moving. In this chapter, we are going to be looking primarily at what we call statics problems. Engineers call them statics problems. Physicists call them statics problems sometimes too. But if you have a friend that's in engineering college and you ask them about statics, they'll tell you that they took an entire class called statics. And it was all about problems like this, examining stationary situations and asking ourselves how big the forces are going to be to keep that situation stationary. And that's extremely important, as we'll see in a couple of the examples, to discuss how strongly we need to build things so that they can do the job we want them to do. So that's what we're going to do. That's the first half of this chapter. The second half is torque and some other things, center of mass. But right now, the discussion is the static problems and all the forces being balanced. And this is going to be a little intense from the math standpoint, probably the most intense math we'll do all semester. We're going to be looking at multiple forces acting on an object, and we're going to ultimately end up having to do a system of equations, two unknowns. Fortunately, that's usually going to turn out to be pretty friendly to us. Usually the solution to that's going to be pretty good. Just like, last couple chapters ago, chapter 4, when we were doing the two-dimensional problems, we kept running into quadratic equations, but we never quite had to use the quadratic formula because something was always zero, which then made it easier for us to solve for the squared term. So here we have a classic example of a statics problem. So we've got this crane, right? And the crane's job is to lift the beam. And the crane does that using a couple of different parts, right? We've got the boom, the part that we probably think of as being the crane, really, that central diagonal part that sticks out from the cab. But then we also have a cable, right? There's a cable that runs out and over the end of the boom and actually is what is attached to the beam. So the question here is, what is the tension in the wire and what is the force on the boom if the beam weighs 6,000 newtons? Now, if we think about this in terms of some of our previous formulas and calculations, this seems like a very, very difficult problem because they've only given us one number and they want us to find two other numbers, even though they only gave us one number. Seems very unfair. But we have this wonderful principle of statics, right? This crane is stationary. The crane is not moving. Currently, the beam is not moving. It doesn't say that it's moving up at 5 meters per second or anything like that. So everything is stationary. So we have this condition of a static equilibrium. Everything's sitting still and nothing is changing. And because we have a static equilibrium, that tells us that all the forces in each direction have to add to zero. Really, all the forces have to add to zero, but it's most easy for us to deal with them in the two perpendicular and therefore independent directions of x and y. So you see here, I have made a chart on the screen, and this is going to be, in my mind, extremely critical to your success in solving any of these problems, is to have this chart. Again, one of the things that can make physics, can make math difficult, is you've got a number of different numbers and a number of different equations you need to use, and you can very quickly get confused and put the wrong thing in the wrong place, and then you're up a creek. So organization is very, very important. So this chart, we have a column for the name of each force that's going to be involved. In this particular problem, we have 3 forces, so I have 3 blanks for names. And then we're going to have the x portion of that force, which we're going to put in the x column, and the y portion, which we're going to put in the y column. And again, this is what's going to be really helpful, because if everything, if we get all the x portions together, we can just add them up, right? Because, if it's 15 newtons to the left and 10 newtons to the right, we can just very simply, add the negative 10 to the positive 15, or subtract, add a negative, subtract a positive. It's the same thing, right? But that's easy for us to do. It's not so easy for us to add vectors that are at funky angles to each other, right? But vectors that are in the same direction are easy for us to put together. So that's why we want to split everything into x's and y's, because then everything's in just two directions. What I want to draw your attention to, though, is that even though we haven't started the problem yet, I've already filled in one row of the chart. And that row is the totals, right? Because that's, again, the type of problem we're doing, a static equilibrium problem, which means all the x forces have to add up to 0. There can't be a net force in the x direction. There can't be a net force in the y direction, okay? So this is where our equal sign comes in. Whatever we have in the x column, 500 minus 300 minus 200, it's all got to add up to 0. And the same is true with the y column. So, right off the bat, we're going to have to be dealing with negative numbers, right? If everything was positive, we couldn't possibly add them to 0. So we're going to have to pay very close attention to what's positive and what's negative. We're going to use our standard convention from their Cartesian coordinates, that to the right is positive and to the left is negative for x and y, and then up is positive and down is negative for the y direction. So the first thing we need to do is figure out what point we are analyzing. And this is really, really important, right? Because when we say we have static equilibrium, it means we have all the forces balanced at a particular point, right? A force is a push or a pull, and it has a direction, but it has to be pushing or pulling something. So we got to pick the critical point where all the forces are acting. And so we look at the diagram, and we're going to have diagrams, all these problems in the lecture, and many of the problems on the homework also, they'll have the diagram drawn for you. And it's simply a matter of figuring out where are all the relevant forces meeting, right? The relevant forces here are the weight of the beam, the tension in the wire, and the force on the boom. So here's the boom, here's the weight of the beam, and here's the wire. So they all meet at point A. That's where they all meet. So that's going to be the point that we are interested in, and we're going to look at all the forces acting on point A. So first of all, we're going to start with the one number they gave us, right? The beam. They told us the weight of the beam. So we draw an arrow from point A pointing straight down, because we know this is the weight of the beam, and gravity pulls things straight down. So the force of the weight of the beam, and we're going to put that in the first column. We're going to call it FW, right? It's a force. And it's the weight force. So we're going to use capital F for force and a lowercase and a subscript W for weight. And that weight is all in the y direction. None of it's in the x, right? Gravity does not pull you side to side. Gravity pulls you straight down. Might feel like gravity's pulling you to the side if you're standing on a hill, but the reality is gravity's pulling you straight down. You're just not up and down. So this is nice, because we have 0 in the x, and then all 6,000 newtons is in the y. But it's down, so we have that negative sign, which I included, which is very important for us to include. So that's our first force. That one was easy. That one we have numbers. There's no unknowns yet. Life is good. The next force we're going to look at is the tension in the wire. The tension in the wire. Please don't get confused. There's also a wire here, yes. But that wire has a tension exactly equal to the weight of the beam, right? Beam's pulling down, wire's pulling up, other part of the wire is pulling down. So when we say the force of weight here, we really mean that's the force in that wire, which has to be equal to the beam, because there's nothing else pulling it down on it. The tension that we are talking about in this problem that we're supposed to solve for is this tension in the top wire, okay? It is pulling to the left on point A, okay? And it is pulling directly to the left. So that's going to be nice too. So we're going to call that the force of tension, capital T for tension. And we're going to put that down here in the chart as well, the force of tension. Now, that tension is pulling entirely to the left, which means it's not pulling up or down at all. So that's going to be a big fat 0 in the y column. But there's a big force in the x direction, and it is all the force of that tension. So we're going to take the name of the force, and that's going to be our variable, and we're going to stick that in the x column as our force tension. It's all pulling, and it's pulling to the left, so we need a negative sign because it's pulling to the left, okay? So those are our first two forces. The last force is the boom force. The boom force is pushing, not pulling, right? If everything was pulling, and we can just take a moment to look at point A and look at our red arrows and think about this, when we're not sure whether the boom pushes or pulls, realize that if the boom pulled, everything would be going the same direction on point A, and point A would move. In order for point A to sit still and remain stationary in its static position, the boom must be pushing out, okay? And the boom is rigid and the boom is under compression. It's being pushed in from both sides, and so it is pushing back on both the cab and on point A. So the force of the boom is up and to the right, and we're going to use a capital subscript B for the force of the boom. Now, we were told here that this angle is 20 degrees. And we could go through the geometry proof, and I'm sure you would all enjoy the review of geometry. But the wire line and this line down here are parallel, and so this is corresponding angles of parallel lines are congruent. I forget what the abbreviation is, but the upshot is that this angle right here is also 20 degrees. Okay, so we've got a diagonal force, so we're going to have to do the vectors. Well, we talked about that on the previous slide. But we're going to review it here. So what do we do at this point? So yes, we have the force of the boom at an angle of 20 degrees. So we need the part of the boom that's in the x and the part of the boom that's in the y. So we're going to solve this with sine and cosine, as we did before. So the y part is going to be the force of the boom, the diagonal magnitude, which is the total force of the boom, which is what we're trying to solve for. So we're going to keep that as our variable because that's what we want to solve for. But it's the hypotenuse times the sine of the angle to give me the y, and it's the hypotenuse times the cosine of the angle to give me the x. So those are the x and the y values, and we can insert them here in our chart and think for a moment about the signs, right? The boom is pushing to the right, which is the positive direction for x, and the boom is pushing up, which is the positive direction for y. So now we have filled out our chart. I am a very strong believer that if you use this chart, by the time the chart is filled out, you are totally done with the physics of the problem. You're not done with the problem. You still have to solve it. But from here, it is purely an algebra exercise. The physics is figuring out how to fill out this chart and how to have the right numbers in the right boxes and understanding that the x column is going to add up to 0 and the y column is going to add up to 0. That's the physics, okay? At this point, we have algebra to do. But before we start the algebra, we're going to do a quick check, right? We want to check ourselves, make sure we don't make a mistake, make sure we're still on track. Our 3x values are going to have to add up to 0, which means we're going to need to have at least one positive number of the bunch and at least one negative number. So we just take a moment before we go any further in the problem and we scan our column and make sure we have a negative and we have at least one positive. We might have 2 negatives and 1 positive, might have 2 positives and 1 negative. We had a more complex problem with 4, 5, or 6 forces. All that matters is that we have at least one of each. Otherwise, you're not going to be able to add to 0 successfully. And the same is true for y. So here we again see there's 1 negative and 1 positive. So that's good. We have not made any obvious errors at this point. So now we're going to have 2 equations. We can add all the x values and get 0. We can add all the y values and get 0. So we have 2 equations. And that's good because as you learned in algebra, in order to solve for an unknown, you have to have an equation. And if you have 2 unknowns, which we do, we don't know the tension and we don't know the force of the boom. We have 2 unknowns. In order to solve for 2 unknowns, you need 2 equations. And we have those 2 equations. We have the x equation, we have the y equation. Now, the question is, which one should we use? And which one should we use first? We're going to have to use them both ultimately, but which one should we use first? So here's all the same information. I just made it a little smaller so we have more space to work. So we got the x column and the y column. So which one should we use first? Well, we have 2 equations, 2 unknowns. We're going to choose the y equation. And that's because the y equation only has one of our variables present, right? Sometimes this isn't going to work. Sometimes both columns will have both equations or both variables, and I'll talk about how to solve that when we get to one like that. But if we look carefully here, we see the force of tension and the force of the boom. They're both present in the x equation. If we look at the y equation, this is just a number, this is just a number, and all we have is the variable force of the boom. So this is really just one equation with one unknown. And so we can use the y equation all by itself to solve for the force of the boom. And then we can plug that value in over here, and then we'll be able to solve for the force of the tension, and then we'll be done. So the first thing you do is you look at two equations, two columns equations. They are both columns and equations. You look for the column that only has one variable. If one of them only has one variable, do that column first. So that's what we're going to do, the y column. So again, everything in the column adds up, and we get a total of 0. So negative 6,000 plus 0 plus the force of the boom times sine of 20 equals 0. And now we proceed to do some algebra, the zeros. We add the 6,000 to both sides. So now we have the force of the boom times the sine of 20 equals 6,000. We divide both sides by the sine 20 to get the force of the boom by itself. So we have 6,000 divided by the sine of 20 equals the force of the boom. And we plug that into our calculator, and you are welcome and should do it yourself. We plug that into our calculator, round to 3 significant figures, and we get 17,500 newtons as the force of the boom. So that's one of the two unknowns we're supposed to solve for. And now we're ready to do the second part. Okay, now we're going to do X, and I just changed colors so that you can kind of keep your two columns straight by doing it in different colors. So for the X, again, we just add all the values up and we get 0. 0 minus the force tension plus the force of the boom times cosine of 20 equals 0. And we start plugging in, right? We have a value for the force of the boom. We don't really have two variables now. One of the variables is known. And so we're going to bring the force of the tension to the other side because it's negative, right? If we add it to both sides, the negative one on the left will disappear, and it will reappear on the right side as a positive value. And then we stick our 17,500 in for the force of the boom. So we got 17,500 times the cosine of 20 equals the force of tension. This is all numbers. I mean, cosine 20 doesn't look like a number to us at first glance. There's letters there. But remember, cosine is simply a mathematical function. And so if we are taking the cosine of a known number, we are really just dealing with a number. So all of this stuff is numbers on the right, all of this is numbers on the left, and we have a single variable on the right, so we can just calculate it on our calculator. 17,500 cosine of 20 gives us 16,400 newtons. So the force of tension is 16,400, and the force of the boom is 17,500. Now, what I would like to point out to you is this is why engineers have to do these problems, right? Because the beam itself only weighed 6,000 newtons. So you might think intuitively, oh, if the thing we're lifting is only 6,000 newtons, then the crane's probably, the crane could hold up 12,000 newtons. It would probably be more than strong enough to lift the beam, right? Because that's double the weight of the beam. Well, turns out that is not true. The boom has to be almost 3 times as strong as the weight of the beam in order for this to work. And the tension in the wire has to be almost 3 times the weight of the beam. And that's kind of, if you remember back to the canal picture I showed you earlier in the lecture, where the guys were both pulling, one left and one right, but both pulling up. That's what's going on here, right? Part of the boom's force is to the right, and the tension is to the left. And so those are canceling each other out, but they have to be there in order for the geometry of this device to work, right? Ultimately, what we would learn if we started messing with the numbers is if you make that angle bigger, if the boom was pointing more straight up, we wouldn't need to have, there wouldn't be as much compressive force in the boom, right? But maybe there's a cliff right here, and the crane really can't get any closer to where it needs to lift the beam, and so this is what is necessary. Also called by engineers finite element analysis. They are analyzing a particular element in the object and examining how much force it has to be able to withstand. And that's extremely important in the manufacturing process. So this was our first one. Hopefully it made sense. If not, you can rewatch this part of the video, or you can go on and watch the next one. As I hope you found already in the first chapters, the first couple of problems are really challenging because you've never seen this before, and then you kind of figure out the process and it gets a little easier. So we're just going to work through a couple more examples of this type of problem, and then I'll let you attempt them on the homework and on the quiz. And then we'll get into the second half of the chapter. Oh, the check, right? So part of our problem solving process, right? We draw the diagram, we read the problem carefully, we write down our knowns. That's part of what our chart is about. We figure out what equations we're going to use. Here, essentially, we're just going to be using these column equations. The sum of the forces must equal 0. But we want to check at the end. And that's one of the nice things about a system of equations is it's very easy to check and see whether you did it right. So in my case, I chose the x values. Just rewrote this equation, 0 minus the force tension plus the force of the boom times cosine of 20. All of these added together is supposed to equal 0. So I take my two answers and I stick them in and I see if it adds up to 0. Now, if you actually stick that in your calculator, what are you going to get? Well, we did a little bit of rounding. So when you stick that in your calculator, you get an answer of, I don't know what it comes out to be, something like 44 newtons or something. And you look at it and you go, well, 44 doesn't equal 0. Well, 44 does equal 0 for this problem, right? I mean, look at how big of a number we're dealing with, right? 17,500, 16,400. We're talking about 5-digit numbers, and you found an answer that was supposed to be 0 that came out as 44 newtons. So you're talking about it being off by less than 1%, right? 1% of 17,500 would be 175. And you found it to be 44. So you found it to be off by roughly 1/8 of a percent. And that is definitely close enough to 0 for our purposes, right? Again, the reason it didn't come out to be exactly 0 is because we rounded. If you had kept all the digits from this number and kept all the digits from this number and you plugged it in, it would come out to be closer to 0. But there would still, there's a trig function, right? It's not always going to come out to be exactly 0. But that's part of common sense, right? Is being able to look at the problem and say, hey, we're counting in thousands, right? If I'm doing a transaction in the thousands of dollars and I'm off by a few pennies or even by a few dollars, it's not that important in the grand scheme of the problem. So now, if we'd done this and we gotten an answer that was 10,000 instead of 0, then we know there's an issue, right? Or even if it was 2,000, we'd know there was an issue because we're off by a significant amount. But 44 is not significant when we're dealing with numbers in the tens of thousands. All right, so here's the next example problem. Again, I would invite you, depending on your level of comfort here, to pause the video and give this one a try before you play the video and see how I explain the problem. A couple of things you will note is that we have the very same chart. Going to see the same chart over and over again, just like in chapter 4 when we had two-dimensional problems. We use that same chart over and over again. We're going to use the same chart. This is the device that helps us keep ourselves straight and solve these problems. So this time we got a box, and it's hanging from a couple of wires that are suspended from the walls at a particular angle, which happens to be 20 degrees again. So we want to know what the tension is in each wire, T1 and T2. So again, the first thing we need to do is figure out where are we going to measure, where are we going to study? What's the point that we're going to look at, put all our forces on? And again, there's only one point where T1, T2, and the weight of the box all come together, and that's point A. So we're going to look at point A. And again, we're going to start with the box. The box is got a weight pulling straight down, 500 pounds. That's easy. It's negative 500 in the y direction, nothing in the x direction. We're going to call that the force of weight again. Then we got T1. T1 is pulling up and to the left. And again, good old geometry, right? We have two horizontal lines here. They're parallel. And this angle here, which they say is 20 degrees, and this angle here are both going to be the same. That's alternate interior angles are congruent. It's been a long time since I took geometry. But I do know that these two angles are supposed to be congruent, and they are. So the 20 degrees can get transferred down here, and we can make ourselves a little triangle. Now, because I wanted to reuse the picture from the previous slide, I actually did this side instead of this side. But it's the same idea. It's just flipped, okay? We're still going to have a diagonal. We're still going to have an angle. And we're going to find the components by using sine and cosine. And as long as that angle is from a horizontal, sine will be the y and cosine will be the x. Now, if the angle had been up here instead, then we'd have to switch those two, right? Because For this angle, the x is opposite. So the x would be the sine and the y would be adjacent. But that's not what we have. We still have the angle here. We'll see one like that a little later. So this is this is the triangle for T2, but for T1, it's the same thing. It's just flipped around the other direction, right? T1 is running this way, so X is running this way and Y this way. So we're going to call that T1, and it's going to be cosine for the X, but we're pulling to the left. So left for X is negative, so we got a negative sign there. But we're going up for Y, and up is positive, so we got a positive, an implied plus there. There's not a negative, we assume it to be positive. And then we move on to T2, which looks a lot like T1, actually the same angles. So we're going to have exactly this triangle. And we're going to see similar expressions for T2, but not quite the same, right? Because T2 is pulling to the right, which is the positive direction for X. So we've got a positive value here and still a positive value for the Y. So now we filled out our chart. Again, we're going to check each column before we go further to make sure we have at least one positive and one negative. At least one positive and one negative. See here we actually have two positives and one negative. But the point is you got to have at least one of each or you won't be able to sum to 0. But we're good. We've got them on both sides. So now we get to go on to actually doing the algebra. At this point we have finished the physics, and now we got to go into the algebra. We've got two equations, an x1 and a y1. We've got two unknowns, t1 and t2. And again, a little bit of confusion from students sometimes about these variables. These variables are actually the magnitude of the vector, right? These red arrows, they have a length. That length is the size, the numerical value of the vector. Okay, so when we stick T1 into an expression, we're calling that or let's do T2 because we can see it here. T2 is the length of the hypotenuse times the cosine of 20. Okay, so T2 is the actual length of the hypotenuse, and that's what we're trying to solve for. What is the magnitude of the tension? The vector has an angle as well, but the angles were given. They're only asking us here for the magnitude. So again, rearrange so we have a little more space. And so which equation should we use? So we have two equations, two unknowns. This time, both of our equations have both variables. So when that happens, see, we got T1, T2, T1, T2. When that happens, we're going to choose the one that has more zeros, and we're going to go with it. So here we've got both variables, but we've got another number. Here we got both variables and a 0. So that's going to make this one easier to solve. So we're going to go with the x one first. So we got 0 minus t1 cosine of 20 plus t2 cosine of 20 equals 0. So we move the negative 1 to the other side, and we get t2 cosine of 20 equals t1 cosine of 20. We divide both sides by the cosine of 20, and it drops on both sides, and we get the expression t2 equals t1. Now, if you had looked at the original problem, you might have been able to guess that. But now we have algebra that tells us that that is, in fact, true. Now, you might be thinking, wait a second, we didn't get a value here. But that's what happens when you have two equations and two unknowns, and the unknowns are in both equations. What you're doing in the first equation is you're solving for one of your variables in terms of the other. So even if this had come out to be t2 equals 5t1, that's still what we wanted to find out. Because now we can sit there and write the second equation. We can write the second equation and we can replace the T2 in the second equation with the T1 value, or how much T2 is equal, how many T1s T2 is equal to. So we took this T2 and we replaced it with T1. So if it had said T2 equals 5T1, then we would have 5T1 in here instead of just T1, okay? And by doing that, we replace our second variable with our first variable, and now this whole expression is in terms of exactly one variable, and so now it can be solved. So that's how a system of equations works. You probably learned other ways of solving a system by elimination or whatever. This is called the substitution method. So we've solved for one variable in terms of the other, and then we substitute into the second equation. We're replacing that T2 with a T1, and now our second equation is in terms of one variable. So we got negative 500 plus T1 sine 20 plus T was T2, but now it's T1 because T2 is equal to T1. t1 sine 20 plus, that plus isn't supposed to be there, equals 0. So now we can move on to the next step. This is essentially x plus x. So x plus x gives us 2x, 2 times t1 sine of 20. We took our negative to the other side to make it positive. So 2 t1 sine 20 is equal to 500. We want to get the t1 by itself. We divide both sides by 2, divide both sides by sine 20. That's going to give us t1 equals 500 over 2 sine 20. And then again, all that stuff on the right is a number. And so our calculator will give us an actual value for that. Comes out to be 731 pounds. So T1 is 731 pounds. And because we learned earlier that T1 was equal to T2, T2 is also 731 pounds. Now again, if this wasn't quite so nice, if it said T2 was equal to 5T1, well, once we had a value for T1, we could still quickly solve, right? 5 times 731 would tell us that T2 was the 3,500 or whatever it came out to be. We could plug our first known variable in to find our second variable. So now we got both of those variables. We do our check real quick, plug those numbers in. Again, amazingly enough, negative 731 times something is equal, added to positive 731 times the same thing, will in fact give us 0. So our check checks out. So another example, again, that's what we're going to do. Just keep working through examples here of these equilibrium problems where the sum of the x forces and the sum of the y forces both have to add up to 0. So this situation is a little bit different. We've got an object hanging, being supported by 2 wires, T1 and T2, but they're not symmetrical like in the last problem. Again, we got a weight force down. We've got T1 straight to the left, and we've got T2 pulling up and to the right with an angle of 50 degrees to the horizontal. We fill out our chart. Again, the weight force is straight down, negative 600. T1 is straight to the left, so that's negative T1 and no y part. And then T2 has the cosine and the sine. It's up and to the right. So to the right is positive. So we got T2 plus T2 cosine of 50, giving us a positive term in the x's. So we've now got a negative and a positive in the x's, which is what we want. And it's upward, so we have a positive T2 sine of 50 in the y's. So again, we take a look at our 2 equations and our 2 unknowns, and we see there's only 1 variable in the y column, while there are 2 in the x. So we're going to go with the y column first. Our negative 600 plus 0 plus our T2 sine 50 equals 0. You're going to notice here the algebra is remarkably similar problem to problem. We're doing the same thing kind of over and over. Yes, it would get much more complicated with more forces. Many real-world situations have a lot more forces. Fortunately, we're not asking you to be engineers or to solve real finite analysis problems yet. We're just working through the process. So we move the 600 to the other side. We divide both sides by the sine 50. And we get the T2 is 783. Now that we have a value for T2, we can go back and do the x values. 0 minus T1 plus T2 cosine 50. The T2 is the 783, so we can stick that in and have only 1 variable. We move the T1 to the other side to get rid of the negative sign. Now we have all numbers on the left and our variable on the right. We'll plug that into our calculator, we get 503. So 783 for T2, 503 for T1. Again, it's interesting, right? T2's a little bit bigger than the weight of our object, but T1 is almost as big as the weight of our object, and it's just in charge of keeping the object from hanging too far away from the wall. Again, we can then stick our numbers back into a check equation, which we're doing the x1 to check because it's got both the variables. Again, you plug that into your calculator, it's gonna come out to be something 1 or slightly less than 1, which when we're talking about hundreds of newtons, 1 or slightly less than 1 is close enough to 0. All right, one more practice problem here. This one, a little bit different. Examine the diagram to the left. What force F is required to keep the 60 kilogram mass in static equilibrium? So they're not actually asking us to solve for T, they just want us to solve for F. So we take a look at this picture. We will notice here that the angle is measured this time from a vertical line instead of a horizontal line. So that's going to change the problem a little bit. The other thing that changes the problem a little bit is that they gave us the mass of the object instead of the weight of the object. So that's going to require an extra step for us. So again, we look at our arrows. We got the weight force down, the force applied that they're just calling F, which I'd rather they actually gave it a better name than that, but that was how the problem was written. And then the tension in the string. So the weight force is straight down, but be careful, 60 kilograms is not a force, so we can't just write 60. Remember, we learned this back in chapter 5. The weight is equal to the mass of the object times the acceleration of gravity on the planet that it is on. And on the Earth, the acceleration of gravity is 9.8 meters per second squared. So we do 60 times 9.8, we get 588 newtons, but it's down, so it's negative 588 newtons because that arrow is down. The F, the applied force, is all in the X and it's to the right, so it's positive. So we just have plus F and then 0 for the Y. And then finally the tension force. And here I underlined the trig functions to drive home the fact that this is different than we would expect. All the other example problems we've done so far, the X value has been cosine and the Y value has been sine. Here they are switched. And again, if you draw, if you look at this little triangle, you will see that sure enough, the horizontal or X piece is opposite of the angle because of which angle they gave us to calculate from, which again, if you thought about this in a physical, a real life situation, that would by far be the easier angle to measure, right? There's a wire measuring what that angle that wire makes from horizontal would be much more difficult, much easier to measure from the vertical, and that's why they gave us the information in that way. But that means we need to reverse our trig functions, right? The y part here is right next to the angle, so that's going to be adjacent. So the y part's going to be cosine, and the x part's going to be sine. Now the x is pulling to the left, so that's a negative x, and the y is pulling up, so that's a positive y. So again, we make a quick check of our equations before we go any further. We got a positive f, a negative t. That checks for the x. We've got a negative 588 and a positive t. That checks for the y. So we've got our chart filled out. Now we got to decide which column we're going to work with. Again, it's a situation where both variables are on one side, but only one is on the other. So we're going to go with y because there's no y component of the f variable. We write it out just as the column is, negative 588 plus 0 plus t cosine of 40, all equals 0. Again, this is the principle. Equilibrium, the sum of the forces must equal 0. I know I keep repeating that, but that is the key concept behind being able to solve these problems. I don't want you to get so deep in the math that you forget about why we're doing what we're doing. We move the 588 to the other side. Divide both sides by cosine of 40. That gives us our t all by itself, and it gives us a number on the other side. So t comes out to be 768 newtons. So we didn't have to solve for t, but in order to solve for f, we had to solve for t anyway. Now we can go back and do the x equation, which has the f in it. And we'll have the value of t, so f will be the only unknown. So we got 0 plus f minus t sine of 40, but our t value is now 768. Plug that in, bring the negative part to the other side. So now we have f equals 768 sine 40, and f is 493 newtons. So I know these are kind of involved problems. Again, I would encourage you to rewatch this video and watch the step-by-step. Especially the first problem where I walked through the steps in spending more time on each step. But go ahead and start working on the homework and try these problems. I think they will become easier with time. Sometimes you get a problem with a few more angles than we have. Again, the principle is equilibrium. The principle is that the sum of the forces must equal 0. Don't get overly frustrated if the book has problems with lots of angles and the angles confuse you. The key is to understand that the sum of the forces in the y and the sum of the forces in the x must be 0. That's what gives us equations. That's what allows us to solve for unknowns. So that's the end of the first half of chapter 7. I will see you back for the second half of chapter 7, where we'll talk about torque and center of mass.